begin section 9, rolling motion. So rolling motion is the combination of translation and rotation. So far we've concentrated mainly on objects that are rotating, rotational motion. So rotational motion would be, for example, the motion of the problem that we saw last week, where block, and then the pulley was rotating. So in that case, pulley is only rotating, not rolling. So this is only rotation. Rotation. Or the swinging type problems that we've seen, like a rod rotated about one end and then swings. So that's also only rotation, you see. But rolling motion would be translation plus rotation. So it'd be like a ball rolling or a cylinder rolling. So the center of mass of the object moves, right? And all the points of the object at the rim of the object rotate as well. So it has a tangential velocity, V tangential, V tangential, V tangential, V tangential. So the object as a whole is moving from one point to another, so that's translating. Then on top of it, it's rotating. So the total velocity, the total at every point at the rim of the object is going to be the sum of V tangential plus VCM. V tangential plus VCM. Here, the total velocity is going to be, the point is going to be going down, V tangential, and then VCM is going to be going like this. So they add up, like you put this to the tip of that, and then you get V at a certain angle, right? And then here, at the contact point, depending on which one is greater, if VCM is larger than V tangential, then the contact point might slide forward. VCM minus V tangential. If they're equal, then the velocity of the contact point will be 0. And then if V tangential is larger, then the contact point might be moving back. That doesn't mean the object is moving back. The object is still moving forward, you see. So we still have VCM. And then the velocity here, we have VCM, V tangential. So when you add them, you get a vector like that, you see. So now we define something known as pure rolling motion. Pure rolling motion, which would be rolling without slipping. Rolling without slipping. So that the requirement for that is for the V center of mass to be equal to V tangential. VCM to be equal to V tangential. Right, so then that would happen if what? A VCM center of mass. So then what would total velocity be? If they're equal to each other, the total velocity at the top point is going to be 2 VCM. The velocity at the center of mass is going to be VCM, and the velocity at the contact point is going to be 0. Velocity total is going to be 0. So that means the object will nicely roll without slipping. You see? If VCM is greater than V tangential, what's going to happen? This vector is bigger, so then if VCM is larger, this is exactly what's going to happen in that case. The velocity here, let's say for example, VCM is 1.5 V tangential, 1.5 times V tangential. So the total velocity here is going to be the sum of the two. So VCM plus V tangential 1.5 plus, it's going to be the sum of 1.5 v tangential plus v tangential, right? Which is going to be, but you know what, let's make this easy number. Let's say VCM is 2v tangential. So what's the total velocity at the top? Then you have v tangential plus VCM. So then that's going to be 3v tangential, right? Which is going to be how many times VCM? V tangential is half of VCM. So then it's going to be 3 over 2 VCM. So this one is going to be VCM. And then what's this going to be? V center of mass minus V tangential, 2 V tangential, 2 V tangential minus V tangential. That's going to be V tangential, which is going to be half VCM. So let's just give this number. If a car is going at 60 miles an hour, the 60 miles an hour, the tires will also be going 60 miles an hour, the center of mass of the tire. But depending on what kind of road it's on, right? If it has a nice rolling motion and it's not slipping, then the top of the tire will be going 120 miles an hour, and the bottom of the tire is going to be going 0, okay? This kind of case is, let's say the car is going 60 miles an hour. What's going to happen? If this is the scenario, that means the VCM is twice V tangential. So in that case, V tangential is 30 miles an hour. V tangential is 30 miles an hour. So basically here we're doing 630 plus 230, right? 30 plus 2 times 30, so that's going to be 90 miles an hour, which is going to be 1.5 times VCM. 1.5 times 60 miles an hour. So in that case, you have the center of mass here going 60 miles an hour. The top is going 90 miles an hour, 1.5 times that. And then the bottom is going what? Let's see here, this is 2 times 30, right? 2 times 30 minus 30. It's going to be 30, which is half of 60. So this point is going to go in half of that. So I'm kind of doing it also by illustrating the length of the vector. This is 1.5 times this vector. This is half times this vector. When would this happen? This would happen in a car in a rain situation. When you brake too hard and the road is wet, the tires will lock, and the contact point between you and the road will start sliding forward. It's a dangerous position to be in, right? What do I do in this situation? He's asking. He forgot his driver's ed lessons. Oh. So what do you do in that case? If this is happening to you. You're driving and then you all of a sudden notice the top of the tire is going at 90, the car is going at 60, and the bottom is going 30. Of course, you're not going to know the details. That's true, a joke. Right? The only thing you'll know is you've lost control of the wheel. You know, it's not reacting to what you're doing. You know, you're braking, it's not stopping, and you know you're not releasing. So right. What do you do? What does the driver's ed say?
Decelerate. Obviously, take your foot off the gas.
So don't decelerate then. You're saying opposite.
I'm not saying. Oh yeah, I'm saying not brake, but stop accelerating. Like stop. Well, you would be decelerating, but I know you're not supposed to hit the gas.
Not gas, but like.
Because you're still going to be accelerating. No, you're not.
Try to slow down, but not take the brake on it, or
Yeah,
you will start sliding.
Yeah, if you hit the brakes, you're going to hydroplane.
So this is basically hydroplaning, right?
Yeah.
Okay, yeah. So hydroplaning. So what are you supposed to do? Take your foot off the brakes, not the gas.
Oh, you stopping in this scenario?
Usually what causes this? Either stopping too hard
No,
or,
okay.
or maybe just losing control. It could be that
Yeah.
it just got wet and something happened and you lost control. But sometimes what causes it is you hit the brakes too hard.
Yeah.
Both scenarios can happen. Some random reason, or maybe you took the brakes too hard. Well, whatever reason it is, even if you took the brake, you hit the brakes too hard, take your foot off the brake. If that's not didn't cause it, then do the next step. Press the brake slowly, then release it.
Pump the brakes.
Pump the brake so kind of slowly. So what you're doing by that is lowering this value little at a time. You know why? What's causing this problem? Your center of mass velocity is larger than your tangential velocity. In this case, the tangential velocity is 30. That means the tires are not rotating fast enough. Because if they were, the car would be going 60 and the tire would also turn at 60 miles an hour at the edge. You see? So if the car is going 60 but this is not turning enough, then it's kind of going like this.
Okay.
You know? You see here? The car is going much faster
that's
than the
true.
rotation of the object.
Okay. So,
Yeah.
So that's what anti-lock brakes do?
Huh?
That's why we have anti-lock brakes. They pump them like really fast.
At anti-lock brakes.
Yeah,
Yeah.
so-
Up, up, up. Yeah.
So that they'll get them to sync up as
To sync up.
Oh,
So what you
okay.
want to do is lower this value. So when you lower this value, it gives the tire kind of sinks down into the ground. Because what's going to happen in this case is what force is the force that's actually making the tire turn, helping it turn. It's the friction force, right?
Right.
So if you will look at the specifics of what's causing that, there's probably some level of water, which is why we call it hydroplaning.
Right.
And that water is not providing enough of a friction force this way. That's what helps the tire turn, you see? So if that friction force is less than what it's supposed to be, then the tire is not turning much. So what causes that? Well, when you broke too hard, the tire locked, and the surface of the water, which is in contact with the tire, is not gonna support it with enough of a friction, so it's not gonna turn as much. So it might turn, but it might turn slower than how fast you're going. So what you need to do is slow down a bit, and then what that will do is the water will still make it rotate, slow down a bit until the thing starts to sink. And so, you know, after a while, let's say, it sinks and then it sinks some more, right? Once it sinks, the friction force of the ground is greater, right, than the water. So now that will cause the tangential velocity to rise from 30 to some value, like 40, let's say. But since in the meantime you've already slowed down, this thing doesn't need to go all the way up to 60. You see? By you slowing down gradually, you've lowered the VCM such that the V tangential has to go a little bit up, and that's it. That's enough for it to be the same, right? So this one speeds it up, and then you yourself slow down the car. So let's say you slow it down to 40 miles an hour. As soon as this thing is also 40 miles an hour, then now you are in control. It's nicely rolling.
So like, I know on my car I have something called a DTSC, and what that does is it uses like the speed sensors, it has an accelerometer under the passenger seat, and it uses a steering wheel position. So that if your car is like going in the wrong, like you're turning right, but your car is going in that direction.
Sliding, the sideways is
Yeah,
sliding.
it'll start it braking for you correctly to try to, so if you're trying to veer off.
Yeah, so you're talking about the side, this way motion,
Yeah,
right?
so it
Yeah.
has the accelerometer to tell if you're going in the wrong direction. It has a steering wheel position to know if that's where you're trying to go.
These are, I mean,
And it has
nowadays,
speed
if you
sensors
think
too.
about it,
Yeah,
our vehicles are computers,
yeah.
literally, you know. They're computers and they're managed by all these equations that
Yeah.
we're talking about. They're managed by all the sensors that we have in them. You know, they're managing speed, velocity, all rotation, all of these. The car, the vehicle that we use, is a manifestation of all our learning, centuries of learning. You know, so it's amazing. Like we built that. You can kind of almost say, if you believe in a God, you can say, why did God create us? Well, God created us to behold us and say, look at the work of my hands. So to glory himself. Why did we build vehicles? So that we could look at it and say, look at what we've accomplished. You know, so why did we, I mean, I'm driving a Tesla now. It's like I look at it and go, oh my God. Mankind, look at what we've done. The rockets that we're sending, SpaceX and stuff, vertically. So we're kind of now mini gods. We're creating these things so that we can behold it and say, look at the work of our hands. So this page shows a little bit of that. So when an object experiences pure translational motion, so that would be the worst case scenario, would be if VCM is 60 and V tangential is 0. That would be pure translation. That would be the worst case scenario. It's not rotating at all. So it's just going, sliding. You never want that, you know. So then that would be, omega would be 0. When an object experiences pure rotational motion, all of its points move at right angles to the radius in a plane perpendicular to the axis of rotation. And then VCM is 0. So that would be the opposite case scenario, would be if V center of mass is less than V tangential, right? So this scenario I call, if VCM is greater than V tangential, I call that car in rain, because that's the typical case of when it happens. And then when VCM is less than V tangential, that means the car's translation is less than rotation. So that would be like your car is going 30 miles an hour, but your tire is rotating at 60 miles an hour. The opposite. You know? So when would that happen?
Sliding?
That one I call car in snow.
Oh, yeah.
What's the difference?
Car in snow.
Oh, that's.
See, the rotation is a lot faster,
The
you-
car-
but the car's not
Oh.
moving forward,
I see.
right?
I see.
Like, can I say on the ice?
Ice would be more like this, car in rain or ice.
Only.
So that's like.
Ice, because you don't have enough surface friction, so it doesn't rotate a lot. Yeah, that's a good example. That's another good example of this. Car in ice or car in rain. But car in snow or sand.
Okay.
Imagine you go on the sand dunes, you know, or on the
So
motorcycle.
on the
you
ice,
know.
it doesn't rotate that much.
It
because
rotates a
there's no-
lot.
Like you
On
get
the
on
ice.
the
stuck in the
snow
mud.
or-
On the ice.
Yeah, on the ice
There's
it's gonna be
friction.
opposite.
Yeah, there's no friction. That's
Yeah.
why it can rotate so much.
So in this case, the total velocity is gonna be what? On the top is gonna be 90, just like this case was 90, right? On the top, it was 90 miles an hour, right? The center of mass is 60, but the bottom is the most difference. That's when you know that it's different. You see? So notice here, what was it? It was 90, 60, then here was 30, right? Because the VCM was larger than V tangential, so on the bottom, it was moving forward, right? Then what happens here? 60 minus 30, so this is gonna be 30. So the contact point is actually moving backwards, right? Because you're burning tires. Oh, that's another example of this. You're
Oh, yeah.
burning tire.
Drifting.
Drifting is the opposite, I think.
No, burning out. Yeah.
I think this is drifting,
That is.
right? Like that.
Yeah, that's exactly.
I don't know how to do that on the Tesla yet.
I'm sure.
But I don't think that's cars meant
It
for.
probably has a computer to stop you.
Right? Car in snow or sand, or burning the tire. Right? So then what happens? So the worst case scenario of this is if V center of mass is 0 and V tangential is 60. Right? So then it would be what? The top would go 60, the center of mass would go nowhere, and the bottom would go 60. You see? So all it's doing is just turning. And that's what they're showing here, you see? Right here, V is r omega. You see here, as you get closer to the axle, the velocity of the tangential velocity decreases. Remember the equation V is r omega? So as you go closer, V is r omega, the center is not moving, and it has no tangential velocity. Plus VCM is 0, right? They should put here VCM. That's also 0, so the tire is not moving forward. And then the contact point is moving back. So if you're behind that car, as it's snow or sand, it's gonna kick up all the snow and sand in your face. You know, dirt,
Yeah.
mud.
Yeah.
So if you're stuck like that, how do you fix it? How do you help the car go forward?
Kitty litter.
Huh?
In the old days, they kept a bag of kitty litter in their trunk.
You're
and they
trying
put
to,
it under
like-
they dig a hole, put the kitty litter in.
Kitty litter, yeah. So you better get a lot of kitty litter. Or get 2x4 planks,
Oh, yeah.
wood planks. So what's that gonna do? How is that wood plank gonna help you? You put it under. As soon as you put it under, wood has more friction than snow, right? So what's gonna do with the wood? The contact point here is going back. The friction force, the static friction force kicks in, right? Oh no, actually kinetic friction kicks in. Remember the definition of kinetic friction is the force between two surfaces that are moving with respect to each other, right? Here, this object is not moving, yeah, but the contact point is moving with respect to the wood, right? And so, which direction will the friction force be on that? It thinks that since it's moving this way, it's gonna exert a friction force that way. Mu Kn. That friction is gonna do what to the rotation? Slow it or speed it? If something is rotating this way very fast and friction comes along,
Slow down.
Slow.
yeah, I say boom, and I go like this, and then you see? So it has two things. The friction pushes it forward, which kind of slows down the rotation, but it also helps the translation. The car starts moving forward, right?
You have to be a long.
Without friction, we couldn't live because we use friction all the time.
You have to be careful that wood doesn't shoot out at like 60 miles an hour though.
Oh, that's true. Yeah. Because it could,
Yeah.
if it's not embedded in the snow.
Yeah, because that's what happens with like kitty litter. It starts being
Yeah.
shot out at a high speed.
So there should be instructions.
Don't stand behind it.
Stand here. Yeah, you don't want to be there. Like, okay, come on, ready on my command. Ready, set, go. Okay. Yeah, so that friction helps to get the motion going, slows down the rotation, but it helps the translation. And then once the two are equal again, then the thing starts to have pure rolling motion after that. So the goal is to have VCM equal to V tangential. So when an object experiences rolling motion, the point of contact with the surface is instantaneously at rest. This is the weird thing. So when an object is rolling without slipping, either without a car in rain or car in snow, the contact point is not moving. That's kind of weird to visualize that. If they're saying the contact point is not moving, then you might say, well, how is the object moving? You know. So if something is rolling like this. Maybe there's a little video that might help us visualize that. Velocity of contact point during rotation.
Just because we consider the bottom part of like the tire the contact point, even if it's not the exact same point. Like that point's actually going around, but we
Yeah.
consider the bottom, so it's always the one wherever it
Yeah.
makes contact.
Yeah. Let's see. These are more lectures. I want to see if there's a simulation. Let's see this one.
Now consider the wheel that is rolling without slipping. And call the addition of velocities, let's call that point P. That the velocity of P is the velocity of the center of mass, and that pointed this way, plus the velocity of the point P as seen in the center of mass frame.
Now,
And
how are we viewing this?
in that
Is he
frame,
drawing
every
on the
single
black,
point
on
the
a
circle.
see-through board? We're on the other side of the
He's the
board?
glass, I think.
Yeah, glasses.
So he writes from there.
And he's writing backward.
Is he writing backwards?
Yeah.
No, he can't be.
As seen in
You know what?
the
There,
ground.
it's done.
Because
to-
if he's on the other side, we would see it as
So,
backwards, wouldn't it be?
consider the
Yeah.
magnitudes of these two terms. The velocity
How?
in the center of mass.
That is weird.
Yeah, you
That
can see the
is-
way he's writing the P.
Equal to
Yeah, maybe.
And we said that the velocity of the center of mass.
Because
we
if
call
they
that
mirrored it, it would be
CM.
backwards, so it
Yeah.
needs to be.
Now, the rolling without slipping condition
He's writing
was
backwards.
that these two
Yeah.
magnitudes.
He's
were
writing
equal.
backwards because look, he said he wrote the R first, then he go like this.
The velocity.
Oh yeah, he's writing backwards so that
in the
when we
center
see it,
of
it's,
frame is equal
oh my
to
God,
the
that's
center
crazy.
mass velocity
Yeah.
of the wheel. And therefore, the velocity.
My videos will never catch up with that because I cannot write backwards.
I wonder if it's like some kind of digital board. No, because you see his hand.
Is in contact with the ground is equal to 0. So what we say is that the contact point
Because he'd be blocking the text.
is instantaneous.
Oh yeah, you're right, he's not blocking the text.
Oh, yeah, so it's like a see-through thing?
Yeah.
Like
it's-
you wrote it normally,
No, I think he's writing backwards.
but they flip the camera, like
Respect.
the thing like the way it's looking.
Oh.
Yeah.
Oh, that's possible.
But then how does his hand equal to where the,
And that's what
The-
really.
why as
is
he's drawing
this
it, how does it
wheel
match up?
That's rolling
Like,
without
that's
slipping.
like-
That's like a mirror.
Is the sum of these two vectors and it's instantaneously at rest with the ground when the wheel is rolling without slipping.
This is an actual physics problem. How is he writing? This is the problem. Take home test. Go
we
figure out.
haven't
how-
learned anything because we're just talking about this.
White is the magnitude of either one.
Okay, this is kind of what I was looking for.
Yeah.
A simulation of that. See? Contact point is not moving.
Oh.
Oh, that's not at all how I pictured it.
And there's a particular name for that path that it takes. You know, the point goes down, up, like that.
Kind of how piston works.
See, momentarily, right there. See, the contact point is not moving. I say, how the object can move then? Well, because another contact point replaces it.
Yeah.
Because you have to visualize there is infinite number of contact points. There's another one here, there's another one here, there's another one here, and they're all making the same kind of path. You take infinite points. So if you just take one contact point, it goes like this. And at that instant, it's not moving. But doesn't mean that the object is not moving, because an instant later, it's already come up already, you know. Boom. Then it moves. And then when it gets to the top, it's going twice the velocity. Okay, nice. So the rolling without slipping, this is the top point going twice the velocity, VCM, and then this contact point is 0. And they say these are other things that have the same kind of physics. Cycloids, trollate cycloid, curtate cycloid, epicycloids, cardioid. The hell all of these, huh? Epicycloids. Sounds interesting. Hmm.
Like a circle within a circle. Oh no.
Oh, circle rolling on a circle, and then this one is inside of a circle. So there's a whole branch of physics, I guess, that deals with this.
Spirograph.
Wow. Maybe the universe is some kind of cycloid like this. I love that.
Yeah, what is one thing?
This is an epicycloid, right? Cycloid, I think, is the regular one, the one that we have.
So this is what they made the spirograph off of. Those little gears where you draw like a pencil on your
Mm-hmm.
graph. Makes
See,
a lot of sense.
cycloid would be,
Hi, and welcome to Demystifying Math. Today we're going to be working on creating parametric equations that represent a
you
cycloid.
might have covered this in
But before we
calculus,
get
did you
started,
guys?
we should
Cycloids?
probably figure out how a cycloid is
Because it's a
created.
parametric equation.
In this picture, we have a circle that's moving along the x-axis. Also, point P is moving around the circle. Notice that as point P moves around the circle, point D has moved that same distance along the x-axis. And this will continue to repeat, creating what we call a cycloid.
That's what
Notice
rolling
that
motion
in
is
this
essentially. It's an
particular problem,
example of a
The
cycloid.
radius of the circle is 1. Let's review what we just saw. The circle has a radius of 1. Point P traces out the path of the cycloid. The distance traveled along the x-axis by point D is equal to the arc length K. So to
If you
get
took a
an
sine
equation
function-
for the cycloid, we need to figure
I'm
out
not sure
what
if
the
this is
coordinates of point
that a
P
sine
are.
function? It
No,
doesn't look like it.
if you took,
Flipped it?
yeah.
Because sine function kind of goes like this more.
The
Well,
coordinates
then
of
you go
point
like-
C
It goes underneath.
are D,
and
comma,
comes
radius.
back up. If you flip
Well, the
the
radius
bottom
in
ones
this
up,
case is
it
1.
would be this, no?
Because sine function
Now I've
sometimes
created
is
a triangle
concave up,
PRC.
sometimes concave down.
Yeah,
What
but
you
you took
should
it
notice
it
is
down
that
and just flipped them
PR
all
Oh,
up.
would it go like that?
is
Yeah,
labeled
'cause
BD.
I was just thinking, 'cause it's
Corresponds
kind of like how the
to
hertz
D
on
on our x
an
coordinate.
electric motor go,
On our
except
x-axis.
it has a negative because it's AC.
If we look at the
So
sine
I
of
think
alpha
if you took,
it's
if you did
equal
like
to
the
the
absolute
opposite,
value of a
which is
sine,
BD,
like the
over the
values
length of
from
the
the sine function, it would-
hypotenuse, which in this case is 1. So the sine of alpha
I mean,
equals
I
1.
saw this kind of questions
We
in
also should
SAT
know
test.
that
In what?
In SAT test,
SAT test, yeah.
yeah.
So, I mean, what they're doing in this page is connecting rolling motion with these other mathematical concepts that we know of. Cycloids would be the regular one, epicycloids, and then let's see, hypocycloids, what is that? Hypocycloids. this video has all three of them.
Hi there guys, welcome back to my channel. This is your friend and tutor Manas Patnaik. Well guys, this time around we're going to be dealing with cycloidal curves. But what the hell is a cycloidal curve? Well, these curves are generated by a fixed point on the circumference of a circle. Circle may be rolling along a straight line, the circle may be rolling outside a circle, circle may be rolling inside a circle. I mean guys, these are the three conditions.
Oh, I think the hypo just may be the one that was inside.
On
This
this
is
point
the-
P reaches here. Fine. This process goes on, this point P comes here. Goes on, it will come over here. And let's move forward. At the apex, now it will start to come down. Okay, so this is for the first half revolution. Fine. Let's keep it going, keep it going, keep it going. And finally, when one revolution is complete, then this point is the start, this is the end. And that's what you call an epicycloid. Fine. Rolling in the clockwise sense, but outside the given circle, also known as the directing circle. One more thing that you guys must realize that we started from this point and we ended over here. And there is some kind of an angle which has been subtended at the center of the directing circle. Fine. And this angle can also be computed with a simple formula, 360 multiplied by small d over capital D or small r over capital R. So this is how you can actually find the angle subtended at the center of the directing circle for one revolution of the rolling or generating circle. So this, guys, was all about epicycloid.
Oh, they're dividing the
Remember,
diameter of
epicycloid
the radius of
rolling
this by the
circle
radius
is
of the hole.
rolling
Yeah.
outside the
Or
directing
you-
circle
yeah.
in the clockwise sense. As far as drawing is concerned, you're gonna have to make only this portion, okay? So this much portion has to be eliminated, something like this. Alright? So whenever you're making an epicycloid, you need to make only this portion. That's it. Now let's move towards hypocycloid. Let's see what it has in store for us. Well, a hypocycloid is the curve generated, again the definition is same, but the only difference being it rolls inside a circle. Alright? Fixed circle is directing and the rolling circle is moving. Alright? So let's do this. So this is capital B with this as the radius. We're gonna have a circle, that's it. And inside which we're gonna make a rolling
What
circle.
program is
something
he
like
using?
this.
Python?
So that's the rolling circle.
Like you
Let's say
use
this rolling circle wants to start from this position and end up somewhere here, having a revolution, one revolution in fact. In that case, it's gonna be revolving in an anti-clockwise sense, alright, something like this. Let me show you how. Anti-clockwise. So this is the point P upon which we need to keep a track on. And as we move forward, you're gonna see that this point P is moving in a certain direction, something like this. Please keep on watching. That's it. Anti-clockwise sense, we keep on moving. And here we have the final point, alright? Now let us join all these points in sequence. We're gonna have what you call a hypocycloid. Again, the angle subtended
It's
over here
much
is going
different
to be,
looking,
the formula for that
graph.
angle is going to be same as we saw in the case of epicycloid.
Look at now.
So that's exactly what you call a hypocycloid. Alright guys, so this
Pretty
is
cool.
the portion which you need to make.
Okay, now let's
That's
go to, they give you here coefficient of rolling resistance. So when an object is rolling without slipping, like this one, only static friction force is in play, not kinetic, because the object, the contact point is not moving, only static. But on top of that, in some cases, you're gonna have rolling friction, right? So if it's like this, let's say, going like this, only static friction. But then you might say, why does it stop eventually? Because what's gonna happen? Static friction is gonna do no work on the system. So why does the marker stop if it only has static friction on it? Do you see? So that's all, I used to think about that always.
Not
If something is rolling without slipping, the contact point is stationary, the only force is what? Static friction force, right? So let's say you have a level plane. So let's say you give it some initial velocity, the initial is 2 meters per second, right? let's say it's in the case of the marker, it's a solid sphere, solid cylinder. Solid cylinder. So what's going to happen? You have static friction that's opposing the motion, right? So static friction is going to want to slow it down, right? So what are the forces here? F is equal to ma, right? So static friction is the only force that's in the horizontal direction. I'm assuming that the plane is level, so it's not down or it's not up, right? So we have here Fs is equal to ma. Okay, what's Fs equal to?
Mu S times N.
Everybody, that's their first reaction, is to say Fs is mu s n. It's wrong, but I'm not angry that he reacted like that, because everybody's reaction is that. Right? Everybody else would have said that. Fs is mu s n, but it's wrong. And mu s n is only when the object is about to slip.
Oh,
Right?
so-
That's the maximum force of static friction.
So that should be negative BV.
No, that's air friction. Ignore air friction on this. Negative BV. No, no air friction. This is static surface friction. So, since this is nicely rolling, like in this kind of a case, it's not on the verge of slipping, right?
Oh.
So it can't be, Fs can't be mu Sn. It's just some number, whatever it needs to be. In other words, what is Fs? Fs is whatever it needs to be such that the object rolls such that the tangential velocity at the tip is equal to the center of mass velocity, so that it experiences no slipping. So Fs is some quantity. But then just from this equation, you don't know what it's equal to. So you need to apply the torque equation on it also. Sum of the torques on the object is I alpha. You see? So what is the torque on the object? Well, the only force causing the torque is the friction force. You see? So then you multiply R by Fs. Which direction is the friction force? There's two ways to say the direction of the friction. You can do the official cross product. You say R crossed into F is into the board for the torque. Or you can say it's a clockwise torque. Why? Because it's going to tend to make the object rotate clockwise. So it's a clockwise torque. So into the board torque is the same as a clockwise torque. You see? So the torque is equal to R times Fs. That's equal to the moment of inertia of the object, right? Which is what? This is a solid cylinder. What axis is it spinning around? The axis that is coming out of the center, which we called IZZ. Remember in the lab? This, the moment of inertia of a cylinder about an axis through the center is half mr squared, IZZ. So that's the moment of inertia of this. So half mr squared alpha. So combining these two equations, we can calculate for our two unknowns. Our unknowns are the acceleration and the Fs, right? So R and the R cancels. Fs is equal to half mr alpha. One of the R's cancels from the moment of inertia. So what is the R alpha? R alpha is the A tangential at the edge. Okay.
Fs is equal to, what's the meaning of this A versus that A?
Oh, I think that you're gonna convert that MA to alpha times R.
Which one?
Fs is equal to M times A.
Here, Fs is Ma. A is the A center of mass. So it's gonna decelerate.
A tangential is yes, that's what I mean. A is equal to R times alpha.
So according to this, if the friction force translationally is fighting against the motion, translationally, right? So what should happen? This acceleration is actually technically a negative ma.
Yeah, going that way.
Yeah, so what should happen to the VCM? If you gave it an initial velocity of 2 meters per second, right?
Yeah, it's gonna slow down.
It should slow down.
Right.
So V final is V initial plus AT. So V initial is gonna be 2 minus Fs over M T. But according to this, what's happening? Fs is actually helping this accelerate, you see? It's causing the velocity of the tangential to speed up. This is kind of tricky, the motion of a ball on a level surface. It's causing the velocity to speed up. So the initial velocity at the edge is gonna be what? If you gave it an initial velocity of 2 meters per second, that's initial velocity is gonna increase. In other words, this is the initial velocity of the center of mass, and this is the initial velocity of the tangential initial velocity, right? So that's gonna be the initial tangential, which is gonna be 2 meters per second. So if you gave it that initial velocity, as you rolled it, then you let go. You see? Then how do we analyze what's gonna happen? The initial velocity at the tangential is gonna increase. So then it's gonna be V initial plus V tangential is gonna be V initial plus A tangential T, and then this one is V, so V final center of mass is V initial center of mass minus A center of mass T. It's better to put CM subscript to everything so you know what you're talking about. V final center of mass is V initial center of mass minus A center of mass T. And then here V final tangential is V initial tangential plus A tangential T, right? So V final tangential is equal to V initial tangential plus A tangential T. So then V final tangential, in our case it's 2, and this is 2 ACM is gonna be what? F over M. Or I should just, you know what, I could put absolute value here, and in here I already put my negative because I know it's slowing down. So ACM is Fs over M. Okay, and then you got here 2 plus a tangential is gonna be 2Fs over MT. So according to that, what's gonna happen? Its center of mass velocity is gonna decrease, right? This center of mass velocity is gonna decrease after a while from 2 to, let's say, 1.5. You see? Then what's gonna happen to the tangential velocity? The tangential velocity is gonna increase from 2 to, let's say, 2.5. But then what's gonna happen to the velocity of the contact point? Is it to the left or to the right?
To the left, right?
Yeah, because this one goes 2.5 this way, and then 1.5 that way, right? 2.5 minus 1.5 is 1. So now the contact point is actually moving, which means kinetic friction kicks in. You see? In other words, a static friction would like to, if there's something is rolling nicely, it would like to speed the object's rotation, but slow the object's translation. But as soon as you do that, the contact point does what? The contact point begins to slide to the left. And now kinetic friction kicks in and pushes the object forward, Fk, doing what? Bringing this back up to 2.0, and then it fights against the rotation, bringing the rotation back to 2.0. So in other words, static friction instantaneously wants to all the time bring it out of pure rotation, but kinetic friction doesn't let it. So according to that, the marker should forever roll nicely. Once it's rolling nicely, it should forever roll, never come out of nice rolling motion. Because if static friction speeds it up too much, kinetic friction slows it down, you see? But then why does it eventually stop?
Air friction.
No, rolling friction.
And rolling.
There's a third kind of friction called rolling friction. And that's why they gave you here the coefficients of rolling friction. You see what I mean? So static friction would try to bring it out of rotation, but kinetic prevents it. So with static and kinetic, the object rolls nicely, the combination of the two. But rolling friction, what does it do? Rolling friction opposes the rotation, but doesn't help the, rolling friction fights against the translation, but does not help the rotation. See, with static friction, it helps the rotation, fights against the translation, you see? But rolling friction, only one directional, no torque. So rolling friction will eventually cause it to slow down, you see? So according to this table, rolling friction is 0.00 bicycle tire on wooden track. So bicycle on wood, smooth concrete, bicycle on asphalt, and bicycle on rough paved road. But you see how small they are? Oh, sorry, this is not the rolling friction force. This is the rolling coefficient of friction. It's mu sub r. Mu sub r. But of course, all of these depend on whether the bicycle tires are pumped or flat. What's going to happen if they're flat? Is the numbers going to go up or down? If the tire is flat, it sits down more on the surface. Friction force goes up, right? If we had that basketball from the other day, we could try it. The pump basketball and the flat basketball, we could roll them. The pump one should go more. So the rolling friction goes down as you pump. That's why when you inflate your car tires, there's an optimum tire pressure you need. So that it's not, you don't want to overblow it because you might blow the tire up. And also it might be too bouncy when you over pump it. And it'll go like this, very, like you go over a little bump and then it makes you jump up too high. But you don't want it to have it flat because rolling friction goes way up when it's flat and you spend more gasoline.
And wear out the tires.
Yeah, you wear out the tires and you spend out more gasoline. So there's an optimum. So if I wanted to do an experiment, I would give this some initial velocity. Let's say I'm giving it 2 meters per second. Determine how far it goes. Let's calculate. Let's see. Okay, it went about the distance of the table. So if I knew the velocity I gave it, I could do an experiment to do, what's this, about 1 meter, 2 meters. Let's say it went 3 meters and then it stopped. So what would be the coefficient of rolling friction in that case?
Okay, I see it now.
So I gave it an initial velocity of 3 meters per second, and it went, no, 2 meters per second. Then it went 3 meters. What would be the equation? So then you have N and mg. You have static friction, but we don't care about the static friction because remember, static friction and kinetic friction offset each other so that they don't do anything here, right? Then rolling friction. So the only force that I'm concerned about is the rolling friction. So then you have Fr is equal to ma, Fr is equal to mu Rn, right? And then N is equal to what? Mg, mm cancel. And then in my case, what happened? V final squared is V initial squared plus 2AD. So V final was 0. V initial squared minus 2AD. So my A is V initial squared over 2D. So it's simple kinematics, what we've done in the first couple chapters. So A is equal to, if I gave it a speed of 2, square it over the distance D, and it went 3 meters, right? So that we can find out what the acceleration, what the deceleration of the car is. 4 over, oh, okay, that's pretty easy to calculate. 2 over 3.667, right? Then you put that over here, you calculate the coefficient of rolling friction. That sounds pretty high, right? According to those numbers. It's about 0.6. .67 or something, you know. That seems high because we want to get a number like 0.002, right? Yeah.
I'm trying to picture this visually. So static friction would be like here. Kinetic when it's pushing off, right? So would rotational be right before it reaches static?
No, they're
Like-
all at the same point. They're all at the contact point.
Right.
Even rolling friction is there, but I'm just not writing it from there. They're all exert their forces at the contact point.
Yeah, but
But
like,
rolling friction only fights against translation.
but like, for instance, this would be static, and
Why are you tilting the other one?
well, I'm just trying to picture it because it's in movement. So let's say contact point. Like in my head, I'm thinking it pushes off this way as it's rotating.
Static?
Yeah, I mean it's a much smaller than but.
Yeah.
So wouldn't rotation be like the point here where it's kind of like, as it's making contact, like,
Oh, I see.
And this pushes off to go forward, right?
Yeah,
And this is doing is static, so it's not doing anything. But when it's coming in contact this way, it's actually fighting the translation, right? I mean, it's in a much smaller scale.
yeah.
But would that be kind of visually how I would try to imagine this? Like, one's like
Rolling
fighting it
and
backwards.
static are always happening, rolling
Right.
and static.
Yeah.
FK is only happening in cases where these are not the same. And like I just argued, the only way this could not be the same is if you started it out to be the same, then kinetic friction, static friction might want to put it away from the being the same. But kinetic friction doesn't let that.
Right.
Okay? But now I could do this. What's going to happen now? Watch this. I could give this an over rotation and then drop the marker. Okay, so are we done with that? So we just did a little experiment to show how to calculate μr. Well, I didn't really know my initial velocity, so that this number might be off, the 2. Let me see, what's more realistic number? Yeah.
The answer is 0.067 or 68.
Oh, is it 0.0?
Yeah, because you have 0.667 divided by 9.8, correct?
Oh, okay. I thought that was too large. Okay, that sounds much better. 0.067. Okay, that's much better. Now, my velocity could have been more because I did give it a pretty good kick. So what if my velocity is like 4 meters per second? Then this would be 4 squared instead of 2 squared. So it would be 16. So this would be 4 times more. Then this would be 4 times less. So 0.01 something. Okay, then we're getting in the region of what it should be. So if we had exact velocity, initial velocity, exact distance, so this would be a good, good little experiment you can do. You can get different balls of different flatnesses, give them the same velocity, determine how far they go, and determine the rolling friction coefficient as a function of flatness, as a function of PSI, pounds per square inch. Then compare basketball to soccer ball to volleyball, all of that, you know. Okay, now the other one I can do is what's happening in this case. I'm gonna give this okay, I'm gonna give this a over rotation, we call that. Over rotation, then drop it. So instead of pushing it, the other one I was going like this and nicely pushing it. So it was already starting out without slipping. Right now I'm doing, oop. Oop. Okay, so what's making it go forward? Okay, so let's come on the board here. So in that case, I'm giving it an over rotation, right? So the marker is like this. And let's say the initial velocity of the tangential velocity is 2 meters per second. And then since I'm dropping it to the ground, the center of mass velocity is 0. So then what's happening? Kinetic friction is kicking in, right? Kinetic friction is pushing it forward. Right? So what is it doing? Kinetic friction is causing the marker to move forward. You see? So F equals ma, what's going to be the equation? Mu Kn is equal to ma. Right? So let's say how long did it take for it to establish its, it probably took about 30, 40 centimeters, right? For it to establish from when I did it. It quickly started rolling nicely. So about this long it took for it to establish its pure rolling motion. So then we're gonna do mu K mg is equal to ma, mm cancel, and then so according to that, what's gonna happen to the VCM velocity? the final center of mass is the initial center of mass plus AT. This is ACM. ACMT. So then the final center of mass, what's the initial center of mass of that marker? I'm just rotating it and dropping it. So VCM initial is 0. It's not moving forward.
Oh, yeah.
You see? So this guy is 0.
Oh,
What's the A? Mu kg. Okay, but now we need another equation for the torque.
oh, yeah.
Torque is I alpha. What's the torque on the system? Well, since the friction force is forward, it's going to cause it to slow down because I gave it an over rotation. You see? It's going to slow down. So what's going to happen? The torque is going to be a negative torque. Negative R times Fk, RFk, is equal to the moment of inertia of a solid cylinder times alpha, R cancel, and then Fk is mu Kn, A tangential. So now I have what? The final tangential equals the initial tangential minus A tangential T. I'm doing similar to what I did when it was pure rolling motion, right? So the final tangential is going to be, the initial tangential is 2, because that's what I gave it, right? Minus A tangential is what? And then this one is going to cancel. I'm just going to take the absolute value here, absolute value. So I'm going to say mu K mg is equal to half m A tangential. MM cancel. Then you have mu kg is equal to half A tangential. So A tangential is 2 mu kg, which is similar to what happened last time because ACM was just mu kg, A tangential was 2 mu kg, right? So then this is 2 mu kgt. So from there, we can determine what? Well, how long will it take? So what's going to happen? As a function of time, the V center of mass is going to increase, and V final tangential is going to decrease, right? Until when? When is pure rolling motion going to be established? When this equals this. So this is going to slow down, the rotation is going to slow down, the translation is going to speed up, you see? So then when they're equal, this goes over there. So T is going to be what? 2 over 3 mu kg. That means this is how much time it's going to take for that marker to achieve pure rolling motion. How many seconds it's going to take. From there, how can we determine the distance that it will have traveled? What's the distance that it will have traveled? How about this one? Right? X final is x initial plus v initial t. What was my v initial of the center of mass? This is center of mass. It's 0, right? Because I just dropped it.
Right.
So this one is 0, this is 0. So the distance it travels is half A center of mass t squared. What's A center of mass? Mu kg. And then t, the condition for t is this. How did we get that? By setting V final tangential equals to V final Cm, right? So then, let's see, A center of mass is going to be that, and then T is going to be that guy squared. So what does that come out? D equals half mu kg, 4/9 mu k squared g squared. So then what is that? D equals 2/9 mu k g. Okay, so now if I already know the distance that it traveled, I can calculate the mu k. So let's say it traveled 30 centimeters. You see? So all I need to do is just a little quick experiment, right on the spot. Rotate it, drop it, let it go, estimate some numbers, and then do my calculations based on that. Right? So the mu k is going to be 2/9.3 times 9.8. Let's see if we get a reasonable result from there, what the mu k is. Let's see.
I feel like we should use a lot of pool table examples in this chapter.
Oh yeah.
Yeah, because that's all English. Like you try to strike a ball and with enough rotational so that the
Yep.
cue ball actually comes back or stays still or goes forward, depending on what you want it to do.
Mu k is 0.07. It's pretty low for a mu k, but it is a marker. It's a nice smooth surface, you know, and that table is smooth too. So again, it goes by. I don't really know if I gave it initial velocity of 2, and I estimated the distance. But the test question can be opposite. It can give you the initial velocity. It can give you the mu k, and then it can say find the distance that it takes for it to establish pure rolling motion. Okay. Now, what's going to happen if I do the opposite? Let's say I give it a push instead of this one. Remember, the first case was I did this. In that case, I established pure rolling motion already. Went forward 2 meters per second and it rotated 2 meters per second. The second one, I just rotated it, then I dropped it. The other one I can do is push it so that it only translates. You see? But then it establishes pure rolling motion. So what's the physics of that? Well, not much different than this. In that case, I'm giving you the VCM of 2 meters per second, and then the initial tangential is 0. So what's the contact point doing? It's not translating, right? So the contact point is just sliding forward at 2 meters per second.
With kinetic friction.
Oh, yes, with V total is going to be 2 meters per second. So now kinetic friction is going to kick in,
Yeah.
right? And kinetic friction is going to say, oh no, I'm not going to let you slide forward. So now kinetic friction goes this way. So what changes here then? This one is still the same. This one is still the same. AT is still 2. And then ACM is still this. But here's the difference. Now I gave this initial velocity a 2. So the equations for ACM and A tangential are the same. So this guy is 2 now, right? Is that true? Now this guy is 2. Plus ACM is what? Mu k GT. Oh. And it's going to slow down. It's going to be negative, right? Because I gave it a kick, since friction is this way, friction is fighting against the translation. You see? So this guy is a negative. But what happens? This is the opposite. Now friction is helping the rotation. Boom, boom. And what's the initial velocity tangential? Starts with the letter Z.
0.
Good job. 0.
Okay, I'm changing it.
Huh? instead of rotating and drop, I push,
Right.
right?
But still,
With tangential, so
Oh,
it's not
yeah, yeah,
spinning.
yeah.
It's not spinning, but it's going forward.
Okay,
That's what it's
so
doing.
now, given the same, let's say, using the same mu k, is it gonna take a farther distance or shorter distance to establish pure rolling motion? The other one took 30 centimeters, we assumed. Or is it gonna take the same distance? I think it's different because one is mu k gt, the other one is 2 mu k gt, so it's not very symmetric.
I would say longer for some reason.
Longer distance?
I think, but I could be wrong.
Okay, well, let's do it. So what's gonna happen? Is this criteria still gonna be the same? You got mu k, so this is 0. So then this one is what? So now I'm gonna set this guy, V final t equals to V final Cm. So V final t is what? Q mu k gt, V final C, 2 minus mu k gt. What's the same? Because this is still 2, just doesn't have this guy. And this is 2, but it's minus here. So you still have 3 mu k gt is equal to 2. T is equal to 2/3 mu k g. Then you put that into D equals,
No, you might be right.
oh no, it's more.
Oh, okay.
It's more because you do have a V initial now. The time is the same. That's it. Your hunch was right.
Yeah. I'm just picturing pool in my head. That's
Yeah,
the
yeah,
reason
yeah,
I can
yeah. You're
figure all this
picturing
out.
pool,
I
yeah,
play a lot of
exactly.
pool.
Yeah, so now you got your V initial is 2 this time, right? Time is 2/3, and then mu k is 0.07, g is 9.8, plus half a is gonna be what? Mu k g, 0.07 times 9 point, oh, what was mu k? Yeah, mu k was 0.07, right? Mu k, so mu k, g, you got here, half a is, mu kg times 2/3 mu kg squared. Ooh, ooh, ooh. It will be farther.
Can you explain like how does this happen? You just like push it without.
You
any-
push it, no, push it at the center so that it doesn't roll. You see?
I mean, at that
Imagine-
moment it doesn't roll.
Yeah, but
Yeah,
eventually it
it's not-
establishes
it's
rolling
not
motion
roll.
because of kinetic friction.
Yeah, and it's
If
not
there was no
rolling.
friction at all, it would just keep sliding.
Picture a pool cue. Like when you hit the ball, it slides along the table for a while before it starts rolling. Like you tap it in the center and it'll start just like skidding along the table till it starts rolling. But if you hit it like up or down, it'll start rotating,
Yeah, right.
you know. Like sometimes if you hit a pool cue, it doesn't even rotate till it strikes another pool ball. It'll just skid
yeah,
across
right.
the table and then hit it and then start rolling.
Hmm.
It's weird, but because there's hardly any friction on the table. But there's not like.
Oh, this is 0.07 times 9.8. This part didn't change, right? Let's see here, half and 9.8 over t squared. So it's gonna be a lot more, 0.07, it says 1.94. Just this part of it came out 1.94 meters. Is that right? Huge, 4/3. 0.07.
What the hell achieves rolling motion?
Plus 0.07. plus 0.3. So the other one we had assumed it establishes rolling motion in 30 centimeters, right?
Right.
With the same mu k, it's going to take 1.79 meters to establish pure rolling motion, right? So visually speaking then, if I drop it and I let go, if I drop it with the same velocity, if it establishes pure rolling motion this fast, let's see. So let's say 30 centimeters establishes pure rolling motion. The other way, I'm pushing it, so it should be about a meter, almost 2 meters.
Yeah.
And you saw that it was more. 'Cause it's going so fast to begin with, right?
Right.
So yeah, it makes sense. See, he pushed it. You notice
Yeah, I
that?
pushed it.
You give it translation motion. And now let's do an object going down an incline. I think they give you a little example of that. Complete the worksheet on the first page, fill each grid, Release an object from rest and let it roll down an incline. Determine the moment of inertia coefficient by timing the trip from top to top. Moment of inertia. The critical angle past which an object will slip rather than roll. Okay, so then they have the object start from a certain angle. They have starting the object. They have a picture? No. They didn't give a picture? Well, yeah. I mean, why am I looking for a picture when I don't sometimes give you pictures? And I say, from the problem you should be able to visualize, right? Well, release an object from rest. So something like this. So this one is from rest, down an incline. So this is angle theta. Determine the moment of inertia coefficient by timing the trip. So if you know, let's say, the height, and you know the distance, right? Time that trip, and you can calculate the moment of inertia of the object, right? When it gets here. So they're using an energy method to calculate it. So they're saying potential energy initial equals final kinetic energy plus final potential kinetic rotation. You see? Remember, the potential energy converts into two kinds of kinetic energies. Okay, so then what are they doing? They say omega is V over R. Why is that? Well, remember, omega is V tangential over R. But if it's pure rolling motion, V tangential and the V center of mass are the same. So technically there should be a V center of mass, right? And then there should be what here? V tangential. You see? But if they're the same, if it's not slipping, then we don't have to write that down. So it's MGH V tangential over R, and then this one is V center of mass squared. V center of mass equals V tangential equals V. You see? So then you get rid of that. So then from there, what do? They're going to calculate the final velocity, right, of the object. Oh no, they're actually calculating for the final, they're calculating for the moment of inertia of the unknown object. So in this case, they never told us what the shape of that object is. We don't know if it's a solid sphere, a cylinder, hoop, but we don't need to know. It could be a mystery object. But you could do this experiment, time it, and you can calculate the experimental moment of inertia without knowing the shape of the object. You see?
That's crazy.
Isn't that crazy? Yeah, so imagine solving for the V here. right? And what did they do? Oh no, my goal is to calculate for I, right? So I'd rather take this and put it here. Divided by what? V squared over 2R. Right? So then what did they do? They factor out the, they divide the 2R. Oh, they take the, let's see, what do they do? Oh, this should be R squared, right? V over R squared. So they take the R squared to the top and the 2 to the top. 2R squared and mgh minus half mv squared over v squared. Then they distribute the R squared inside. Oh no, they keep the R squared outside. They factor out the m. They distribute the 2 inside. 2gh minus v squared, right? Over v squared. Is that what they have? Yeah. Mr squared, 2gh over v squared, minus 1. Okay, then divided by v squared. Let's see. So if you calculate, okay, from there, what are they gonna do? Here's the coefficient. It still needs a bit of work. So, what they mean by coefficient is this number in front of the mr squared. Remember moment of inertia of a cylinder, sphere, hoop, they're all something times mr squared, right? That something tells you whether it's a solid sphere or a hollow sphere, right? So if it's a solid cylinder, then the moment of inertia is half mr squared. If it's a hollow cylinder, what's the coefficient? Moment of inertia is mr squared. So the coefficient is 1. If it's a solid sphere, 2/5 mr squared. Right? If it's a hollow sphere, 2/3 mr squared. Coefficient is 2/3. Right? So in our case, what's the coefficient? Well, you see, mr squared, we already know it should always be mr squared. So this is the thing in front. So they're calling that alpha. That's the coefficient in front of the mr squared, right? So then they say, recall that for an object accelerating uniformly from rest, its final speed is twice its average speed. And so the final speed is twice the distance divided by the time. So in other words, they're just going to use the kinematics. They're going to say final velocity is initial velocity plus a times t. So if initial velocity is 0, this is v final, this is a. What are they trying to solve for? Oh, and then a is going to be what? The acceleration of the object, right? V final is going to be. Oh, how about the other one? Oh, not this one. Oh, this is better, yeah. The final squared is twice the acceleration times the distance, right? Twice the acceleration. H is equal to S t squared. Or 2a times the distance. Oh, and then how are the distance and the height related? We can say sine of theta is h over d, right? H over d. So then we can say d is equal to h over sine theta. So v final squared is 2a h over sine theta. Right, then we can put that into that alpha, right? 2 times g times h, and then v final squared is 2a h over sine theta. So 2h cancel. Alpha is equal to what? G sine theta over a minus 1. So the term in the front is the g sine theta over a minus 1. So if you wanted to do this experimentally, how would you calculate the acceleration? So all you would need to do is let it fall, time how many seconds it's taking to reach the bottom, and acceleration would be twice the length that it went over the time, right? A is equal to, remember the lab that we did, lab 10 with rolling motion? V final is equal to 2 length over time, and then acceleration was what? Final, V initial, V average was, we did V average was length over time. V final is 2 length over time. And then acceleration is equal to 2 length over time squared. Yeah, so then twice the distance over the time squared. So if you're doing this experimentally, you have a mystery object, you let it fall down, time it, then you do twice the length that it went divided by the time squared, that it would give you the acceleration. Then you would do 9.8 times sine of the angle over the acceleration that you got. And how did you get the acceleration? Twice the length over the time squared. You see? Minus 1, that would give you the coefficient. So if it was a solid sphere, this coefficient should come out around 0.4, because it's 2/5. If it's a hollow sphere, it should come out 0.67. You see? And then so on. Now, how would you theoretically calculate what the alpha should be? If you want to do theoretical, then you would have to calculate what the theoretical A is. What is the theoretical A when a solid sphere comes down and when a hollow sphere comes down? Right, so the experimental A is by just timing it and doing twice the length over t squared, right? The theoretical A is to say, well, what shape are you making go down? If it's a block, what's the acceleration of a block as it's coming down? And then imagine there's no kinetic friction, right? So then you have mg sine theta minus is equal to ma, and then A is equal to g sine theta. So the theoretical acceleration for a block, if there's no friction, is what? G sine theta. Therefore, what's the alpha? What was the alpha? G sine theta over A minus 1. So what's the A for a block? G sine theta, right? What's G sine theta over G sine theta minus 1? Huh? G sine theta over G sine theta minus 1 is 0. Therefore, a block doesn't have any moment of inertia.
Oh, yeah.
Because it's not a rolling object.
Yeah. You got me with that one.
Yes. Right? Now, what's the theoretical A for a solid sphere or one of the other ones? Right? How do you calculate that? Let's say it's solid sphere. Then you have M, mg, and what's the friction force? Static friction force. You can't have without any friction like a block. Block can slide down without friction, but this guy can't. So you need Fs. Right? So then in the translation sense, you got mg sine theta, and then frictional force is fighting against that, right? Then what? Then you got the torques on the system. What are torques on the system? Well, the only force causing a torque is the friction. So torque is equal to I alpha, FSR is equal to, what's the moment of inertia of the sphere? Right? 2/5 mr squared alpha, and then the R and the R cancel. Fs is 2/5 ma tangential, and then A tangential is going to be the same as A. Then you substitute that into this Fs. Over is so important, Ma. So in other words, for an object, for a solid sphere to rotate nicely without slipping, there must at least be this much friction force on it. 2/5 times the mass times its acceleration for it to roll. But then you take that and you put it into here, and you calculate the appropriate acceleration that it needs to have so that it can roll. You see? It's like a circular argument. It needs this much friction for it to roll, and the acceleration for it to roll is this, right? So then you're gonna have mg sine theta, this one 7/5 ma, A is 5/7 g sine theta. So this is the theoretical acceleration that it should have, and the way to calculate the experimental acceleration, 2 times the length that it went over the time squared, right? So this would be the experimental run if you did it, and that would be the theoretical. But if I take the theoretical A and I put it into this equation.
I have a question.
Yeah.
Like, there is actually an angle between where. No, never mind. Okay, I see. Okay.
You see that?
Yeah, I see it. Okay. So you plug in.
So now if I take this A theoretical 5/7 g sine theta and I put it here, that's going to give me back to my original question what that alpha is of the solid sphere. So g sine theta over 5/7 g sine theta minus 1. What is that going to be?
2/5. Oh.
Sweet. Right? Coefficient, back to the coefficient of the, in front of the mr squared is the 2/5, right? So which of these two wins when you race a solid sphere with a block of ice without any friction? Who wins? When you race them down the track. The acceleration of the sphere is 5/7 g sine theta. The acceleration of the block is g sine theta.
Blocks, because nothing's getting translated?
Yeah, the block wins.
Because there's no
The
friction.
acceleration is larger. Okay? Now, you might say, why? There's 2 ways to explain it.
There's
One,
only
block,
friction.
there is no friction
Yeah. and-
force. For a sphere, you need friction for it to roll.
Right.
But because friction is helping it to rotate, it's fighting against the translation.
Yeah.
So you're gaining something, but you're losing something. So should cars be built with tires that are cubical then,
Without any friction?
without any friction?
No. Then how
Because
you
it's
stop?
easier, because you don't have to rotate it.
Then how you stop?
How would you go?
We can't visualize
Well,
that.
if it was frictionless, you would just need the energy behind you to push
Just
forward.
sort of push it forward.
But he's right, you'd have to have energy in front of it to brake, so it'd almost be like the fan boats, where they just have like a giant fan on a boat.
Yeah.
Oh, like
Pushes
that.
them forward, but you'd have to spin around to stop, to have, I don't know how you'd spin.
Yeah, but you see the acceleration is larger. So here, there's no friction force to slow it down. Here, friction force slows it down but helps rotate it. The other way to put it here, is to say the potential energy of this only has to go into translational energy of the block. Here, the potential energy has to diversify itself. It has to go into kinetic energy and potential energy. But just like we say in the advising community, when you put your money in, diversify. Put some into stocks and mutual funds, right? Here, the potential energy is smart. Some of its money it puts into rotational kinetic energy, which is mutual funds, and some of the money it puts into translational, which is stocks.
So, if for instance there were no static friction, that was also a frictionless surface,
It wouldn't roll.
it wouldn't roll, so they'd be the same.
Oh yeah, exactly. It wouldn't roll, then it would be the same.
Okay.
So the next question that they ask is, the second question is best solved using Newton's laws of motion. What was the second question that they asked? They asked the critical angle past which an object will slip rather than roll. So in other words, if I start increasing this angle, what's going to happen? I'm decreasing the normal force, right?
Yeah.
So at a certain point, I don't have enough normal force and it starts slipping. So what's the largest angle that I can have? So how do I solve that? Then I go back to this equation, to the friction force. Remember, the friction force that you need to have is 2/5 MA, right? But then what's the maximum friction that you can have? Is mu Sn, right? So you set the friction force that you should have equal to the friction force that you can have, right? And therefore, what's the equation for the normal force? What was the equation for the acceleration? 5/7 g sine theta, right?
Oh, can you explain it like real quick? So why is like the A center of mass is equal to the tangential?
Oh, because it's pure rolling motion, it's not slipping.
Oh, it's not. Okay.
Yeah. So I'm setting here the friction force that it should have to the friction force, to the maximum friction force that it can have. But when I'm tilting it, the more I'm tilting, I'm reducing the normal force. It's getting dangerous, you see? So then you have here mu s. What's the equation for the normal force from chapter 5? mg cosine theta, right? So what's going to happen? Combine them and get an equation for the greatest angle. So 5 mg cancel. You have 2/7 sine theta equals mu s cosine theta. All right, let's see what equation they came up with here. Tangent theta is 1 plus mu times 1 plus 1 over alpha. So in our case, we're going to get what? Tangent theta is mu s 7/2 mu s, depending on what that alpha coefficient was, right? So if it's a sphere, what was that coefficient alpha? 0.4, right? 1 plus 1 over 0.4 is 7/5. So that's what we're getting. It's not, 7/2. So 7/2 times mu s. So after that angle, if you increase it, it's just going to slip, right? So let's just say the mu s is 0.5. What number would that come out? Tangent theta 7/2 times 0.5. tangent theta is 7. So that's still pretty steep, because tangent at 45 degrees is 1. All right? So what is that, something like 70 degrees? Tangent inverse of 7.
Like that.
Yeah, that means you can tilt it. See, you can tilt it at a great angle.
Yeah.
So that one is for a sphere, but a cylinder is different, right? So if I tilt it at a large angle,
Yeah.
you see, then it's just gonna slip down. You know, you can kind of see. When you go too high, you don't have enough friction force for it to roll. And of course, if it's on the vertical plane, can you kick that one?
There's another one, right?
If it's on the vertical plane, will it ever roll?
No.
What's the normal force?
0? No.
N is 0, right? If there's no N, there's no friction. It can't roll.
Yeah.
You see? So what did that angle come out?
Our US is 0.5, correct?
Huh?
Our US is.
0.5, yeah.
All right, I got 60.
Yeah, okay, that's good. So you can raise it to 60 degrees or something. Okay, we'll continue with rolling motion on Wednesday, then we'll start torques and angular momentum. Great stuff.
Okay, so they were right